Hello, everyone. Hi, this is
Hello, hello.
Hey, Gregory. Hey, Scott. Great. For everybody, for our audience, good morning, good evening, depending on where you are. And welcome to AI on Chain podcast, actually, podcast 3 with Professor Gregory. And we're very honored to have Gregory to join the podcast today. And very quick background about him is Gregory is the founder and CEO of Piquare. He's also a tenured professor of computer science at University of Illinois Urbana-Champaign, UIUC, in short, and a former NASA engineer, where he also developed the K framework, open source framework for programming language semantics. And that's also where and also actually before Piquare, he was a pioneer of a form of verification and funded runtime verification. It's now the leading form of verification company in Web3, and that is also where like Piquare origin come from. And in 2023, he founded a Piquare with a vision to solve fragmentation and trust limitation in today's blockchain infrastructure. So welcome, Gregory, and if you like, feel free to give a self intro as well.
Thank
and
you. Thank you so much, Chief, for the kind introduction. Yeah, so as you said, I'm a professor of computer science, but my specialty is programming languages, and specifically what we call formal semantics, which is the most mathematical of them all, where programming languages or computation models in general are defined very rigorously as mathematical theories. And why we do that? Not because we want to make our life complicated, but because that's the only way to talk rigorously or very, very seriously about correctness. Without a formal definition, a formal mathematical theory of the programming language or computational model, it is virtually and technically, mathematically impossible to even define correctness. It all boils down to just moving hands then. But with a mathematical definition, then we can very rigorously talk about what things do and then prove that they do indeed what they are supposed to do. And yes, I started my career as a mathematician back in Romania. I grew up in Romania, and mathematics was everything back then, and chess, and then Go later on. Then I came to the United States for PhD at UC San Diego, and then I moved to NASA in 2000. I spent 2 years there, and I learned that there is a big need for a language framework that allows us to actually do what I said before easily. And then I moved to academia, to UIUC in 2002, and worked on the K framework. But the idea was planted at NASA, seeing the pain my colleagues there went through when trying to prove everything correct, because NASA really needs everything to be correct. And then, yeah, in 2010, started runtime verification. And then 2020, you said 23, but it was really late December. So it's 24 when we started Pi Squared. Yeah. So thank you for inviting me.
So, Professor Gregory, I think we have a very deep root in UIUC mafia in crypto world. I know Professor Pramod was your colleague from Sentient. It was your colleague. And then if you look at Suran from Eigenlayer was your PhD student. And then we have Elon, the founder of the Mega, is also your student. I actually, my personally, I also come from UIUC, but I wonder, from your opinion, what do you think actually, has such a presence of UIUC in crypto world?
It's interesting because we don't even teach blockchain at university. I proposed the first course on blockchain this semester, and I just finished it now. Now is the finals week. So that was the first course on blockchain, right, in our department. And yet, as you said, many students were produced in our department. Amazing, amazing Web3. Yes, Ilong, founder of MegaETH. Philip Dayan, also founder of Flashbots. He was also my student. and Yilong, they spent many years working with me, and also in runtime verification. And then Shiram Kanan, yes, he was not my student directly, but also a student in our department. And you as well, right? And many others. So I think what makes UIUC a great place for beautiful minds is same like other top universities like Berkeley also, and Stanford and MIT. But I think particularly UIUC puts a lot of emphasis on two things. One is mathematical rigor of algorithms of everything. We don't publish papers until they are really done well. And another one I think is also kind of unique to UIUC, having been at other places as well, is the very friendly collegial atmosphere in the department, where people are encouraged to collaborate, and lots of collaborative class projects, and students encouraged to do amazing things. But other universities also do it. I think what's different at UIUC is that may sound weird, but basically students cannot do much else because, as you know, UIUC is pretty much in the middle of nowhere, how many people say, and people have each other, right? And that creates a strong bond.
Yeah, I think one point I would argue is that comparing to Stanford, particularly, Stanford, I think UIUC has a deeper presence in system and distributed system. That's probably one other reason as well. At the end of the day, I think blockchain is a part of the distributed system.
Yeah, so there are different, of course, rankings, but different criteria. I think what UIUC wins with is publications and citations, right? Not as much on grants and funding, but a lot on the. There is a website called csrankings.org where you can check rankings of different computer science departments by different criteria, and yeah, so the depth of results and publications is what comes from our department, and of course with that lots of talented students. And I think once you have a strong background in mathematical rigor of computer science related topics, be it hardware, software, AI, systems, then it's very easy, not very, but easy to adapt those to different areas. I think it takes you only one or 2 months. A person like you, Scott, it should take you, educated at our university, it should take you only 2 or 3 months tops, right, to become a Web3 expert. Even if you know nothing about Web3, because Web3 is not that difficult once you have all the background to understand it.
So from my perspective, I feel like it's different than the big data distributed system or AI distributed system. Is that it has a different assumption. It's just like you cannot trust the peer node in the system. But I agree. I think underlying is a lot of philosophy. When we design the theory is similar.
And thinking the process, right?
The logical reasoning process.
Exactly. Right, and dealing with a challenge. And enjoying dealing with a challenge.
That makes sense. Actually, that's why I'm also curious. Like with Gregory, all the background and again all those like a form of application, mathematics training, and everything you had. What makes you what inspired you to build like Piquare basically starting from last year? And what exactly is Piquare solving, and why it matters so much right now? Like basically, why would you start Piquare now? Yeah.
Yes, that's the question, the best question. So I've done formal semantics and formal methods all my career and programming languages. And runtime verification was starting in 2010, before blockchain was a thing. And the main customers of runtime verification were mission critical entities like NASA, Boeing, Toyota. We helped them prove mathematically that their programs did what they were supposed to do. Then in 2017, we started working with blockchain companies at runtime verification, with Ethereum Foundation, with Cardano, with Algorand, and many others. And if I could say so, we've seen all the mess in the Web3 domain, from the most basic consensus protocols all the way to the craziest programming languages that were used for smart contracts, and all the errors. And we found errors in critical components. And don't take me wrong, all these errors actually were good business for runtime verification because everybody wanted to have their protocols audited, make sure that they are not error prone. But one thing that started growing inside me was this firm belief that we are not doing things right in this field, in the Web3 domain, starting with the blockchain concept itself, right, which solves a major problem, double spending, as we learned from Satoshi Nakamoto, and then was copied in all the other blockchains afterwards in different shapes and forms. But in the end, the same fundamental idea that if we have a total order on all the transactions, then we avoid double spending. And that comes at a huge cost, which is exactly the feature it offers, total ordering. Because of the total ordering, you cannot go above certain limits in terms of performance, especially how we will need very soon for AI agents. I think very soon we'll need AI agents to be able to make payments and settle transactions at amazing speeds. 1 million transactions per second will be too little. It will be a lot more than that. Right? Everybody will have a few agents working for them at the same time very soon, and agents working for each other. Okay, so existing performance of blockchains, putting aside correctness. So suppose that they are correct. They are not, but suppose that they are correct. Everything they do is correct. They are formally verified and everything. Then just the performance will be too low for the needs in the future. But the reason I created Piquare was to do things what we call correct by construction. Right? So there are two approaches to correctness in the world of formal methods. One is to build a system, then have models, mathematical models for different things in the system, and then prove that the system is correct. That's called formal verification. Right? So we formally verify the system against properties that we want the system to have. That's the traditional approach to correctness. But there is another way, a better way. What if we can push a button and generate the system from its specifications to be already correct? We call this correctness by construction. It's constructed to be correct. And now with the advance of AI, this is more and more feasible because I can build a system I can generate the system using the state of the art in optimizations and efficiency and parallelism and everything in the world of computation. And then the AI models may help us build also mathematical proof of it as it is being generated. Because if you generate the system in a certain way, you know why you generate it that way. And an AI agent following the process could help with constructing also mathematical proof of it. And then to have everything correct by construction. And we started with program executions. That was, I think the idea started in 2020 when I proposed for the first time that we can actually reduce computation in any programming language. We can reduce it to mathematical proof completely automatically. And then we can check that mathematical proof with a specialized proof checker. And that will give you the ultimate correctness guarantee by construction for program executions. It's like verifiable computing, but verifiable computing plus because it's universal, works with all programming languages, and it's also correct by construction because you can extract the mathematical proof of the execution of the program directly from the formal semantics of the programming language in which that program is implemented. Okay? And that can happen completely automatically without any extra effort. Of course, you need all the engineering, all the tools to be in place, and took 20 plus years to develop this tool arsenal. But now it's there. And that's why, to answer your question, why now, Chi, is because now that framework, the K framework, is ready for this. Now we can take real programs in real programming languages and execute them with these mathematical models and generate mathematical proofs of their correct execution according to the language semantics. And at the same time, verify those mathematical proofs. So this way you don't have to trust compilers, you don't have to trust interpreters. Again, all these bugs in this were good business for runtime verification. But once I realized that the technology is there, then now we can actually avoid all these problems in compilers, interpreters. Then the idea of Piquare took shape. Let's start a new company where things will be always, anything that is claimed to be true will always come with a mathematical proof. And that proof will be checked. And once you check the mathematical proof, then you can generate a different proof, a cryptographic proof, that yes, the mathematical proof was there, it was checked, and it passed the check. So now I have the succinct argument why the claim is true. You see, mathematical proofs are wonderful, and they are truly, but they are huge, potentially huge. And I cannot ship to you a mathematical proof because the mathematical proof can be a terabyte in size if you go, because mathematical proofs go all the way to the axioms, if you want them to be very rigorous, the axioms of mathematics, the atoms of the universe, of reasoning and logic, right? So that mathematical argument, in spite of its, strength and irrefutability, it's too big. But if I check it with a zero-knowledge circuit, I can generate a ZK proof that the mathematical proof is correct. Okay, and that's why Piquare, proof of proof, cryptographic proof of mathematical proof.
Yeah, I think, Professor, this part is very interesting. That I wonder. Actually, you described tons of have several steps here. I wonder if this K framework is actually in parallel with compiler, or is part of compiler step, or is how's the relationship with compiler here? I actually a little bit confused here.
Right. So very good question. So it is a compiler and it is not a compiler, and it is an interpreter and it is not an interpreter. Okay. And by the way, it's been a lot of the work on the K framework has been done in collaboration with my colleagues at UIUC, other professors like Vikram Adve, who is an expert in compilers, and he created LLVM, the LLVM language framework, and several of the students who work in his team at LLVM, now they joined Piquare, and they actually work with us on the K framework. So we think K framework is a layer above LLVM, which brings the programming languages to LLVM. Okay, so if you have now a definition, let's say, of Python in the K framework, and by the way, there is a definition of Python in the K framework that was a master thesis of Dwight, who is also working at Piquare. So if you have the formal semantics of Piquare, let's say in K, now what you can do with the K framework, push different buttons and do different things with Python programs, like, for example, executing them or translating them to another language or formally verifying Python. So think of the K framework as a menu from which you choose different tools that you want to apply on a certain language. But what is different is that everything K does will generate under the hood a mathematical proof that that thing that it did is correct according to the mathematical definition of the programming language. For example, let's take Python again. Suppose that you have an AI agent implemented in Python, okay? And we have a Python semantics. You can execute that using the conventional, compiler interpreter pipeline, right? You compile maybe Python to WASM, and then you execute using a WASM interpreter, let's say, right? Or other languages. But with the K framework, there's a different pipeline. I take the program. First, before that, I push a button. I have the formal semantics of Python. I push a button, and I generate an execution model of Python. Okay, and that behaves like any interpreter of Python. Now I can take any Python program, in particular the AI agent, and execute it with this interpreter that is generated from the mathematical definition of Python. And I get the same result, let's say 42, as if you execute it on the other pipeline. Okay, and what is different now is that on this conventional, traditional pipeline, you have to trust a lot of things. You have to trust the compiler from Python to, let's say, WASM. Then you have to trust the WASM interpreter. And who knows what else? If you also want to generate a ZK proof, you also have to trust now some ZK VM, on top of all this. So if you calculate how many lines of code you really have to trust, you may end up having to trust millions, if not tens of millions of lines of code in total that you trust with the execution of that program. On this other side, with the formal semantics, what happens? You get the result 42. And what will happen under the hood is that as the program executes, imagine like you have a very rigorous log, execution log, where every single step in the execution is a mathematical proof step, mathematical evidence that that step was executed correctly according to the definition of the Python program. Okay? And then I get the result 42. And what literally happens here is that a mathematical theorem, program equals 42, was proved rigorously using the actual definition of the Python language. So the trust base now is only the Python semantics. And of course, you will say also the K framework, the button that I pushed, because I have to trust what he did. But no, because if you have a proof checker, a mathematical proof checker, and that's completely generic, has nothing to do with the K framework or Python or Java or anything, just verifies mathematical proofs. 1 + 2 = 2. Alpha implies beta, implies beta. Alpha implies beta, and alpha implies beta, modus ponens. Right? So there are very, very basic mathematical proof steps that can be checked with a proof checker, mathematical proof checker, which is unbelievably small. Think like a few hundred lines of code. In a few hundred lines of code, in any programming language, you can implement a proof checker that can check any mathematical proof. And now what the K framework does, it generates a mathematical proof. Now you check that mathematical proof. And now the trust base has been reduced from millions or tens of millions of lines of code to only 400 or 500 lines of code, which is the proof checker. Of course, you still have to trust the semantics of Python, the definition of Python. But that's unavoidable. You have to trust that anyway. Even if you go on this, because otherwise, what is Python? Even if you go to the traditional pipeline, you still need the formal semantics of Python if you want to prove anything about this pipeline. If you want to prove, for example, formally verify the compiler. Actually, for formally verify the compiler, you need the semantics of Python and the semantics of the target language, let's say WASM. And then you also have to prove that the compiler is correct. It's a nightmare. One PhD is not enough, okay, to prove to formally verify a compiler.
Yeah. Wow. First of all, Gregory, thanks for the lecture. This is actually very very informative. Honestly, I have not studied this much before, but definitely the value prop here to me is very clear in terms of, like you said, the new approach that now you guys so-called this correctness by construction, reduce the trust needs and volume from the old millions of lines of code now to the original, semantic language semantic like Python,
Yes.
which is hundreds of lines of code. So I actually have because apparently now I'm serving as a CEO in the company, and a lot of times I have to think about the business value here.
Yes.
And this is where I'm curious more on what does that mean to the customers or the users who are using you guys, because you mentioned a few keywords that caught my attention, and I want to kind of dig into that a bit more. So one is, again, I got the point that now you the trust base, or the trust needs reduced a lot.
Yes, the trust base minimized. Yeah.
And the second is when you talk about performance, you specifically especially mention the future of agentic internet or agentic words would require agent to be able to pay and settle in truly real-time manner.
Yes.
So in this case, why that will be how would you guys be able to really facilitate that part? I guess that's one.
Yeah.
And the second is, you also mentioned the mathematical proof and the cryptographic proof. That's cryptographic proof is helping reduce, again, the size of the proof
Yes.
to people a lot. would that also be part of the reason why it can be further facilitate the speed and performance? Yeah, sorry, I just had a lot of questions about.
No, lots of good questions. All of these are very good questions, and I don't have answers to all of them, but I have answers to some of them.
Okay.
Let's see. So what is the value proposition from a business perspective? Why is this important? So first of all, as you said, the trust base is minimized. Now you only reduce it to the formal semantics of the programming language, which is unavoidable. You have to trust something. You have to trust the programming language. And a proof checker, which is very, very small, only a few hundred lines of code. And the proof checker is so small that anybody can implement it very quickly. Actually, if you're a student in my class on programming languages, you will have to implement it as a class project, one of the first class projects. It's so easy to implement. You implement it in the morning, right? It's just a switch statement with 12 cases because the mathematics has only 12 proof rules, the mathematical logic in which this is implemented. So the trust base is minimized. In terms of performance used to be the killer. For a long time, performance was very, very poor until 1 year or so ago, when things improved a lot because of a lot of engineering in the K framework. So now we got to a point where the performance, for example, for EVM, the performance of K EVM, which is the interpreter generated from the EVM semantics, is comparable or even outperforms GET at this point. Okay, and that may look unnatural because how can you generate an execution engine from a mathematical definition which is as fast as an actual handwritten interpreter? And the answer there is just engineering, a lot of engineering in the framework. And by the way, the same happens with compilers these days. You can, of course, always write a program in assembly, which will be faster than in C, let's say. But how many people can write a program in assembly faster than what C generates or the C compiler generates? Very, very few, because the C compilers take advantage of fetching, prefetching, speculation, and different layers of cache, and so on and so forth. It's very hard to compete with that when you write by hand programs in assembly. Same here. You can write an interpreter, actually GET is an interpreter, right, for EVM, but you cannot beat the amazing optimizations that are being done these days in frameworks, like the K framework. Okay, for example, how to decide what rule applies next. You can do a binary search on bits. So there's an algorithm called based on automata, on decision trees, called pattern match automata, which makes it really, really fast. So anyway, I'm telling you this because I, started to systematically explain to everybody I'm talking to about formal semantics that performance is not an issue anymore. It used to be an issue, but it is not the issue anymore with formal semantics. So that also it's another way to answer why now, because of all this engineering. And then there is also the ZK part. So ZK allows us to actually defer computation, right, from on-chain to off-chain, right? We can do computation off-chain, get a proof, and then come on-chain and only commit the result of the computation after we verify the proof. All right, so the same can be done with mathematical proofs and ZK proofs, but you can do it with mathematical proofs even without ZK proofs. ZK proofs are not ready yet, are not ready for AI. No matter what anybody will say, I know it, you know it. They are not ready for AI. It will probably take a few more years before they are truly ready for AI. But with the Piquare network, what you can do is to get mathematical proofs for what agents do. Okay, so we can execute the agent, get a mathematical proof without the cost of generating a ZK proof. But then the question is, how can you get a mathematical proof so you can verify it? Right, with the ZK proof is small. You can get it and verify it and then deploy. But with mathematical proofs, how can you get the mathematical proof? Of course, if you pay the cost, you can maybe get it, but that's huge. Could be a big proof. But what we can do instead is to have a network, and that's what Piquare does, a network of verifiers, right? So what they do, they generate the mathematical proof and verify it. And like any decentralized network of verifiers, once you have quorum on these verifiers, once you get enough thumbs up from them, you know that execution was correct mathematically because they verified it and because the semantics of the programming language is public. And this way, you get confirmation that what happened was correct. Okay.
I guess, Professor, you actually mentioned two steps here. So first is that I don't know if you answered the question for Chi's business question, but I think you mentioned two steps here. First is that you have some, your past research generates this mathematical proof, and then from mathematical proof you generate a proof of proof in this case. And then I wonder that how does that process work? And then second is that I feel like this can be huge disruptive for all the existing ZK approach in this case. Like I feel like you're proposing a way to completely disrupt ZK approach from certain perspective.
Totally. I actually firmly believe that the existing ZK VM based approaches will not last too long. Just to be even more controversial here. No matter how great they are, and I have friends in all these teams, Series 0, SP1. I think they do amazing work, but I think the approach will not last.
So I think in this case you just use proposing a formal verification, use mathematical way to replace all the ZK proof approach, basically.
Yes.
But I wonder from the mathematical proof to proof of proof, is that that part is still part of ZK proof, or is that part not ZK proof also?
So now, okay, good question. So let's first like we discussed before the K versus traditional compiler approach. They discussed the existing traditional ZKVM approach. Okay, so what you have to do, you still have to compile your program, let's say from Python to RISC-V. Okay, and now you can run on the resulting RISC-V binary, you can run a ZKVM for RISC-V, like RISC-0 or SP1 or others. Okay, and then you'll get a ZK proof that your program evaluated to 42. I was about to say correctly, but let's dissect it a bit. What correctly means here, right? So first of all, suppose that your program was very simple, just return 42. Okay, in Python. When you compile it to RISC-V, you will get a lot of instructions. Actually, we did some measurements. You increase the number of steps, computational steps, by 160 times on average from Python to RISC-V. Okay, so one instruction in Python becomes like 160 instructions in RISC-V due to the compiler. Okay, good. So now the first question in terms of correctness is, why should I trust this compiler? Maybe return 42 is simple enough, right, to trust it. But if you have 20,000 lines of Python and you compile it into 2 million lines of code or instructions in RISC-V, why should you trust it? Okay, so that needs to be formally verified if you really, really want to trust it. And then you need the semantics of Python, the semantics of RISC-V, and so on and so forth. Right, so that's the first part. The second part now, you take the RISC-V program binary and pass it to a ZKVM for RISC-V. That ZKVM has likely more than 100,000 lines of code, very complex code, very, very complex code. We looked into these codes. They are probably some of the most non-trivial codes ever written by humans in the ZKVMs. And if there is anything certain about any program larger than 10,000 lines of code or so, is that it has bugs. All right. So now you have to trust also that ZKVM, right, with your life, basically, right? Because you produce a certificate and now you trust blindly. Say, okay, that certificate proves that the program evaluates to 42. Okay, so you have to trust the compiler, you have to trust the ZKVM. All right, now let's go to this mathematical-based approach. Okay, so what we do, execute the program, return 42 directly with Python. There is no translation to anything else. We execute it directly with the formal semantics of Python, which is just one step. Return 42, one step, not 160 steps. Okay, good. And now that execution generates a mathematical proof of this exact program, of this exact theorem that program evaluates to 42. Okay, which will be smaller as a mathematical artifact than whatever you get here in that compilation and execution of the program to this other pipeline. All right, so now I have a mathematical definition, Python. I have a theorem, program averages to 42, and I have a proof of that theorem. Okay. Now to check that mathematical proof, you either trust K, and you don't want to trust K, right? Because it's also a big system, so likely has bugs, or you check the mathematical proof that is generated when you log this program execution. And that mathematical proof, now this is the important thing, can be checked with this proof checker. Think of the proof checker as a Rust program. Let's pick another language. Rust program, 400 lines of Rust, because that's what it is actually. It's 400 lines of Rust. With 400 lines of Rust, now I can check the mathematical proof. Of course, I still have to trust these 400 lines of Rust, but I don't have to trust compilers, ZK VMs, and so on. Okay, good. So this is step number one. This is still not done because I still have to send to you the mathematical proof if you have the Rust proof checker. But this is where ZK comes into the picture. Now the universal ZK comes into the picture. Let's suppose that we implement this Rust program, this 400 lines of Rust program, as a ZK circuit. Okay, think of it as a ZK VM for mathematics. Okay, not ZK VM for RISC-V, not ZK VM for WASM, not for Python, just for mathematics in general. Okay, and now we can check the mathematical proof with this ZK circuit for mathematics, and we'll get a proof, a cryptographic proof that the mathematical proof is correct, right? The second pi in pi squared, right? The ZK proof of the mathematical proof. Okay, and that's it. You got exactly the same result as with traditional, conventional, verifiable computing. I take a program in a programming language, I compile it to something, I get a ZK proof in the end when I execute the program. But here I don't compile it to anything. And now you don't compile to mathematics, right? When you execute it as semantics, you don't compile to mathematics. You execute it with the semantics, and you get a mathematical proof that that execution was correct, right? It's not a translation of the program to anything else. It's not like translating program to K. No, K executes. K is like a meta interpreter, if you want, that executes the program directly in this programming language and generates a mathematical proof. So what is now different here compared to the traditional verifiable computing approach, which we call verifiable computing 1.0, because it's specific to one language, right? And it still has to be formally verified and so on. We call our approach verifiable computing 2.0, because the next generation, where you have only one circuit to rule them all, one circuit for mathematics, that gives you now ZK proof for all program executions in all programming languages without any compilers or translators, right? Directly from their definition of the languages. And that was the main idea. We published this idea first in 2020, so 5 years ago, and then the rest was just engineering, and we realized that, wait a minute, this can be done actually practically. It can be implemented efficiently. And that's the basis, right, for pi squared.
Go ahead, Scott.
Oh, so I was some random thought. I found another UIUC alumni, which is actually a great Web3 founder, Ivan from Sui. The reason is that Gregory, you work with Vikram. Vikram, the Chris Lattice, is inventor of LLVM, which run which basically the compiler run every single Apple device. Chris Lattice, after graduation, go to Apple, and he's the lead engineer, work with Ivan. Ivan is the lead engineering manager to push LLVM in Apple. So that's why it's we found another.
Very flat. Another person that you mentioned is Anatoly Yakovenko, the founder of Solana, also from UIUC.
Oh,
I don't know that part.
Very cool. Yeah, actually, Gregory. So I really like. Because again, this is such a good lecture for me to learn this. And the one thing that's one relevant question I have here is, as you say, that's because what you guys are doing basically allow you to be able to seamlessly translate those language to, or be able to just build a system on hundreds of different type of languages.
Yes.
So my question, and but I remember in the very beginning of this conversation, you also mentioned that the mature of AI models and agents makes it very easy to do some engineering work, or I'm not sure what type of engineering work is that relevant to, like a language, like help you to write, convert the language between like Python to Vasa, the Wasm, or it's not. So actually, this is where I'm a little bit lost here. Like, is that whole thing that you guys are building can be working without any AI help? And if not, then where AI can really help? I think that is the part that I think I'm not very, yeah.
So there are many different levels of this question and where this approach can help AI. So first, let's say the most obvious would be that you can have domain-specific languages for AI models. You can now think more relaxed and more open-mindedly about domain-specific languages. Right? Many times in many domains, not only AI, right? We force ourselves to write a program in, let's pick Java because it's an, independent, interesting language, right? You force yourself to write an interesting program, an important program for your application in Java, but you have to shift your mind to Java setting, right? And you make lots of trade-offs in your domain because of Java. And not only that is error prone, but that also increases the granularity of the computation. You may need to do, again, like I said before, 100 steps in Java for one step, one conceptual step in your model. But if you have domain-specific languages, now you can give the semantics of directly those constructs in your domain-specific language, like train on this data for this kind of feature. Right? And then once you have the semantics of that, first you avoid the artificial work of encoding your models in some ad hoc programming language. Okay? Second, you avoid the probability to introduce errors in that encoding. Right? And then you will actually in the end have fewer computational steps, mathematically speaking, in the execution of your program that you need to prove in order to verify your inference or fine-tuning or whatever the compute was about, right? So that's a first thing that you can do, right? You can define your languages and be a bit more relaxed and more inviting to domain-specific languages and programming languages for AI models. Then second is performance of generating proofs, right, this way, because you get smaller mathematical proofs than actual executions in RISC-V, right, and you have better performance. So correctness, performance. And I would say there is a third argument with respect to performance, which actually I'd like to challenge you with that. So I think that AI agents, the reason AI agents come to Web3, they don't come for blockchain. Okay, let me make this strong assumption, not claim, right? They don't come for the blockchain. They come for two things. They come for payments. They need a payment system, and they come for settlement, right? They want to be able to settle the record. Say, I've done this for you, so you have to pay me, and so on and so forth, right? So settlement and payments, and not for all the other amazing features of blockchains, like a total ordering of all the transactions. I mean, if you have payment systems that do not double spend, right, then it's okay, right? You shouldn't care about total ordering. Actually, total ordering is a problem because now millions of agents have to stay in line, basically, right? Even if the blockchains will give you like 100,000 transactions per second, they're still way too slow, right? Yeah, so what blockchains have in addition to this, right? So verifiability, I call that safety. We call that safety, right? That's the safety guarantee that everything is verifiable. I know I can find information. And the payment system is a payments safety. And there is also the liveness aspect, which is nice about blockchains, right? You know that your transaction will eventually be taken, you will not be censored, and all that. I don't think those are super critical for agents, because agents are little dictators, right? So the agent decides when it's time to execute something, or the user of the agent, right? They don't need an intermediary, right, between them. They can just simply execute, produce a new result, settle it, pay for it, and done. And that's what our network actually provides. Our network is massively, we call it embarrassingly in the field of parallel computing. It's embarrassingly parallel, right? So every single claim that is made on our network, be the fact that that Python program evaluates to 42, that AI agent inferred something, or that user U paid agent A something, one token, all of these are just claims. And our protocol, our network is decentralized, first of all, but then the protocol is not a conventional blockchain consensus protocol. It's just a settlement protocol. So all these claims can be settled completely in parallel and independently of each other. And that's what this will enable. Will enable a new future in Web3, where applications that don't really need the total ordering guarantee of blockchains will unleash themselves.
I think in this case, I think this is also from the fast paper from the Meta, right? So that's
Yes.
published a few years ago.
Yeah.
I found that it's actually, I think I listened, I heard from you in this case, you think this is one of the best paper in the last few years. I saw this paper also inspires Swiss approach in this case.
Yes.
You have shared object, you have this dedicated
Single owner,
object,
single
and
owner
then
writer.
yeah, and then similar with Mega is in this case. Like this is actually one of the foundation paper for the
Yes.
work, both for Sui and Mega
There
is.
was another paper actually before that, published by a team at EPFL in Switzerland. Very, very nice paper. That was the one that proved for the first time that you don't need a total ordering in order to avoid double spending. Okay, but it was too complicated. And then FastPay applied it to just payments. Okay, and actually that paper also included the idea in Sui, the single
Yeah.
writer. They call it single writer protocol. Right, if there is a single writer for something, then you can settle that particular claim that I wrote something completely independently of everybody else. So much faster. And what we do with our algorithm, actually we call it fast set. Okay, from fast settlement. So we generalize FastPay and the single writer, single owner object paradigm, put them together. But we have a more general notion of a claim. A claim can be a payment, can be writing a location, can be other things, can be, Pythagoras theorem. That's a claim, a fact. Or I am Scott Shee, okay, and this is the proof. That's a claim as well, okay? So all these claims, they can be settled, and there is a notion of independence of claims. Okay, as far as two claims are independent, they can be settled completely independent of each other. And payments, facts, writing a particular location that only belongs to you, right? So all these are independent claims of each other. And we have a protocol that works with such general assertions, and that is what powers our decentralized network.
I do feel like, if we're going to onboard the next billion people to blockchain, we don't really need a blockchain in this case, because what's a possibility? You have random two people interact, or random two people, maybe have some inference call, some payment transaction, actually has correlation with each other. It's zero in this case. You don't need a blockchain. You need like a distributed system, as you mentioned, a settlement layer to make sure execute fast and execute in this case in micro batch type of stuff.
Exactly. And actually blockchains can be implemented actually a lot easier now on top of such an architecture, on such an infrastructure. Because really a blockchain, now if you step back and try to reconstruct the concept of a blockchain, what is a blockchain? And you will realize that a blockchain, and I know I'm abstracting it too much maybe by saying that, but it's really just a bunch of computers playing dice. The semantics of playing dice is that somebody will propose a random number and the others will agree that it is the random number. Okay? And that's what happens. So imagine this. Imagine that we had God. Okay? Let's say give us a random number every second. And I say God because God will have no interest, in our world. right? And it will be a fair random number that nobody can guess, nobody can predict, right? So then we can implement Bitcoin completely differently in any blockchain, right? So people can submit transactions every second, then when the random number comes, deterministically based on that random number, we'll pick an order of the transactions. For example, we can sort their hashes with a random number and then sort them, let's say, something like that, right? That's a deterministic way to sort them. And nobody disagrees, right? And then we can have a block time of 1 second for Bitcoin. And it will also be safer, zero energy consumption, right? So that's what a blockchain becomes. So if you have now verifiable random functions and random number generators like random number beacon chains, then you can very easily now implement blockchains on top of the infrastructure by simply allowing people to submit transactions that you want to be totally ordered for some reason, right, to that one particular receiver that will verifiably sort all of them based on a random number. Anyway, so we can go into this detail, but that's what happened in science in general, right? So amazing concepts were invented, but they were combining lots of good ideas together, right? And then we started looking into it, scientists, and dissecting and putting them aside, and we realized that, hey, actually, this is an interesting component in itself. And this is also very interesting and powerful in itself. Oh, actually, now we can build these separately, separation of concerns, the golden principle, separate concerns, and now we can reconstruct what we had initially much better and more modularly and faster, right, ways. So yeah, I think that's what happens with the blockchain right now.
Yeah. So actually, I'm curious, like Gregory, based on what you described, are you considering even like using the basically go out, right? Like have other people, other industries besides just blockchain industry adopt your technology? Because like you mentioned, for example, when it comes to AI agents, you talked about how agents come to blockchain for really the two reasons is payment and settlement.
Yeah.
Of course, like Scott and I discussed this before. We probably have some more items we think blockchain is very helpful, such as like smart contracts for control, like a better control permissions you can add onto that, and the delegation rights and all this stuff. But I really like how you like boil down to simple two terms like a payments and settlement.
Mm-hmm.
So in that case, yeah, actually, like also Scott pointed out, you don't need a blockchain to make this technology be useful to other industries.
Exactly. That being said, we are not actually exclusive. We do not. Actually, we even introduced a new term that we call TVU, total value unlocked, right? So we are not for locking value and fragmentation. We are actually completely against that. And we do not want to isolate ourselves from blockchains. On the exact contrary, actually what we do, we bring all the other blockchains together through Piquare. How? By generating claims and proving them that correspond to their blocks. Okay, we have that for Ethereum, for Bitcoin, and we are doing it for a few other blockchains. All right, so any block in a blockchain becomes a claim saying I go from state 1 to state 2 with this code. Okay, it's just a claim now that is verifiable completely independently of the other blocks. There is no order anymore now because I already have the states. Right now, once you have verified that claim and settle it, now you have a mirroring of the actual blockchain activity on the decentralized network as a claim. And agents now that work, let's say, on or that are integrated with our decentralized network can actually check those without having to go to the Bitcoin or Ethereum or Avalanche or Algorand or Cardano or any particular blockchain. They will see everything in that world of claims, and they can even now creatively implement applications and UIs where you can do payments on Avalanche, let's say, right, and then do the activity and settlement on Piquare. Okay, because if once you do the payment on Avalanche, because of the mirroring, you see exactly that happened on the Piquare network, and now you can settle or take the action, do the inference or the compute because it's being paid for, or you can top up. Maybe you can have an account in your payment system on Piquare, but they can do the top up right on Avalanche. That can pay to to the agent's account, right, on the Avalanche, and then the agent will do work for you on the Piquare network. So this way you can unleash actually the the imagination to write cross-chain applications without actually bridges, without moving assets around, right? So you don't have to. It's not like. I think it will be a gradual transition. I don't think once this is up, then all the blockchains make no sense anymore. Far from it. I think
So
they're great.
I can definitely see the grand vision here. I think, Gregor, you propose a way to have a global settlement layer. In this case, this bridge all chains together, and also in this case, going to be completely out-compete the ZK-based approach, because mathematical is much better than ZK. From certain perspective, mathematical proof is much better than ZK approach.
Yes, long term, I firmly believe it. But short term, again, we'll also support proofs. And we do support proofs in all other ZK VMs. Actually, we implemented our proof checker in 7 different ZK VMs. And I'm very grateful to the ZK VM colleagues who actually helped us, RISC-0, SP1, Cairo. We spent a lot of hours with them to help us implement our mathematical proof checker in their ZK VM in the best possible way. What that means is that now you can make claims that come with proofs in, let's say, Cairo, or with proofs in RISC-0 ZK VM, right? And those will also be settled just as well. So applications are free to choose what counts as a good proof for them. For example, one thing that we're exploring with you that we forgot to mention is doing the computation of AI agents in TEs, right, in trusting environments, because those are better than nothing. Some people don't like them, but I think they're pretty okay-ish. And they give you a proof that nobody tampered with the code that implemented the model. And that proof is okay for many applications to count as the proof that the computation is correct, right? Maybe a ZK proof is better conceptually, a mathematical proof even better. But, considering that those are expensive to produce, a TE could be just good enough, or could be even a good business model for a particular application on top of Kite AI to do that, because they will sell TEs, and there are other things that you can do with them. But anyway, we try to keep a very open mind with respect to what a proof is, and let applications choose what the acceptable proofs are for them.
That's amazing. Thank you so much, Gregory. This again, thanks for this grand vision. And most importantly, it's not just a vision; it's actually something that's you guys already implemented out. It's already have something that people can check out and use. As what we are trying to leverage Piquare for the verification piece that we are doing to really help. For example, like we chatted about the AI agent, we also firmly believe that blockchain-based technology can really serve as a good solution for like the transaction, being the transaction layer for the future agentic internet, which right now we're doing this joint effort with you guys to make that happen. Yeah, we are almost at the end of we're already at the end of the podcast. I'm wondering like where people can find you, like socials, like LinkedIn.
Just search for my name, Gregory Rosu, and my ID is usually at Gregory Rosu or at Rosu Grigore on Twitter, Telegram. Yes, easy to find me. And Piquare, find the company. Go to pi2.network and read about what we do. And feel free to contact us. We are very, very, inclusive. Would like to collaborate and bring many applications to the Piquare network.
Yeah, that's amazing. That's amazing. So, any final thoughts or any like final takeaways you want to share with people? Yeah.
I would say AI is amazing. I was not a big believer initially. I'm a Go player, but as soon as I started losing games, I took it very seriously. And now I believe that that there is a very powerful bidirectional integration of formal semantics and AI, where they can help each other more than the sum of the parts. Formal semantics can help AI demonstrate that they are compliant, that they do what they are supposed to do rigorously. And at the same time, AI agents can help formal semantics produce mathematical proofs. Because I think where an agent can do an amazing game of Go and beat a professional player, right, at Go, such an agent should be able to also generate a mathematical proof for something that was constructed in a certain way that is visible. Everybody can see how it was constructed, right? So humans should not do mathematical proofs. They should come up with ideas, but not mathematical proofs. I think agents will help us on that front. I think we have an amazing future in front of us.
Totally agree. Not only, like Gregory people who are building in the blockchain space, even like the AI people recognize that. Just like, a few days ago, the OpenAI CPO even was talking about how they envision the future of AI agents will be using smart contract digital wallets to manage their spending, manage their permissions and everything. So I think I'm very glad that these two industries are, like really finding the angle, the real world utility angle to converge, than just like us, more like the financial side. I think that's awesome. Thank you so much. Really appreciate your time today, and I hope that the audience are enjoying that. And definitely, there's a lot of like very very hardcore, insightful lectures that I'm probably gonna have to listen back again to digest.
Thank you so much.
Yeah,
Also for the question, very good questions.
yeah, thank you so much. Really appreciate that, and enjoy the rest of your day.
You too.
Okay, bye-bye. Yeah, talk soon.
Bye.